It is my pleasure to give a talk here about the applications of machine learning in financial markets. So basically, the talk will be divided into two parts. The first part, I want to talk about some fundamental knowledge of machine learning, which I hope could help us to understand the mechanism behind machine learning. The second part, I will talk about machine learning in financial modeling with using Python examples. Right, so let's start. So, one second, how can we minimize? Okay, so because we need to understand what is machine learning exactly before using the technology. So machine learning can be broadly defined as computational method using experience to improve performance or to make accurate predictions. Experience here refers to the past information available to the learner, which typically takes the form of electronic data collected and made available for analysis. These data could be in the form of digitized human-labeled training sets or other types of information obtained through interaction with the environment. In all cases, its quality and size are crucial to the success of the prediction made by the learner. I think it is quite easy to understand. I believe you all tried different machine learning approaches before. So when you tried machine learning approaches, you can easily see that if you use a high quality data, you can get better results. And if you keep increasing the size of your training sample, you could get also better results. But what is the mechanism behind these two things? So I hope today I will provide some information about it. So machine learning consists of designing efficient and accurate prediction algorithms. So in machine learning, critical measures of the quality of these algorithms are their time complexity, space complexity, and sample complexity, which is utilized to evaluate the sample size required for the algorithm to learn a family of concepts. So because when we talk about machine learning, sometimes we confuse it with statistical learning or simply statistics. An example would be in statistics, a commonly used model is regression. But in machine learning, there is also a model called regression. And if you only look at the functional form of the regression, you may not recognize any differences between these two, between the same model applied in different scenarios. But so one thing we have to know is that machine learning and statistical learning are different. So in the sense that when you implement statistical learning approaches, usually use different statistics to evaluate the result. For instance, R-squared value, right? P-value, T-statistics, confidence intervals, those are commonly used statistics. However, in machine learning technique, these statistics are not considered. There are different approaches to evaluate, to measure the accuracy of the machine learning model, such as time complexity, space complexity, and sample complexity. So I will talk about these complexities later. So since the success of learning algorithms depends on the data used, machine learning is inherently related to data analysis, mathematics, and statistics. More generally, learning techniques are data-driven method, combining fundamental concepts in computer science with ideas from mathematics, statistics, and optimization. So here I list some problems that machine learning focuses. For instance, natural language processing, which is quite popular since the revision of the DeepSeek. Computer vision also is important, especially for automatic driving. computational biology, it is also an important approach for doctors and pharmacists to build a new medications, because they use, for instance, they use a neural network to search different combinations of proteins to create new medications to cure cancer, for instance. And financial mathematics, it is also a huge industry. So you want to use different mathematical tools to construct either trading strategies or portfolio optimization approach to maximize your return. There are some tasks in machine learning, for instance, classification, regression, ranking, clustering, dimensionality reduction. This is an important one because nowadays, when you try to model something, the model could be very complicated in the sense that the input space is huge. It is impossible in general to use all of the information that you have. Therefore, you need to first filter out the important features. Then you send those filtered feature into some machine learning model. So dimensionality reduction is also important. You can think feature selection is a subset of this topic. So now there are some different scenarios. For instance, I believe you all know these things like supervised learning, unsupervised learning, right? And online learning, which is the scenario involves multiple rounds where training and testing phases are intermixed. And also reinforcement learning, it is the training and the testing phases are intermixed as well. To collect information, the agent actively interacts with the environment and in some cases affects the environment and receive immediate reward for each action. So you can see from this plot, the object of the learner is to maximize the reward over the course of actions and iterations with the environment. However, no long-term reward feedback is provided by the environment. The learner is faced with the exploration versus exploitation dilemma, since he must choose between exploring unknown actions to gain more information versus exploiting the information already collected. And of course, a deep learning, which focuses on utilizing neural network to perform tasks such as classification, regression, and representation learning. And using deep learning, you can combine with those different scenarios, such as supervised learning or unsupervised learning. So with the basic introduction about what is machine learning and what tasks and problems could be resolved by machine learning, we want to understand now why when we use machine learning, we can actually learn the model can actually learn something. So in other words, how can we define the problem is learnable? Therefore, I want to briefly talk about the learning theory a little bit, so that we can try to tear up the mysterious veil of machine learning. So when you actually use machine learning model, you can be sure that the model, the return, the output generated by your machine learning model is the thing that you want to learn, and the results can be trusted. So after knowing the introduction, the basic definition about machine learning, several fundamental questions arise when designing and analyzing algorithms that learn from examples, such as how can we know the problem is learnable? What can be learned efficiently? What is inherently hard to learn? How many examples are needed to learn successfully? Is there a general model of learning? So these questions can be formalized and addressed by introducing the probably approximately correct learning framework, which is called a PAC learning framework, which helps to define the class of learnable concepts in terms of number of sample points needed to achieve a approximate solution, sample complexity, and the time and space complexity of the learning algorithm, which depends on the costs of the computational representation of the concepts. So I'm going to define some basic notations that I will use. So X here is the input space. So you can think it is the data that you send to your machine learning model, and Y is the label, is the target. So it is the output space, and C is the concept. The concept is a mapping from your input to your output. So it is a function, as you can think. It is a function. A class of concept class is just a collection of different concepts that we want to learn, and we also assume that the samples, the instance from this input space, are independently and identically distributed according to some fixed but unknown distribution. Then the learning problem is then formulated as follows. So the learner and you, for instance, the learner considers a fixed set of possible concepts, H, which is a subset of the concept class. And the learner receives samples. This is the input, independently and identically drawn from the fixed but unknown distribution, as well as the label, which is the output that you have, which are based on a specific target concept to learn. The task is then to use the labeled sample to select a hypothesis from the hypothesis set that has a small generalization error with respect to the concept. So this is quite easy to understand, right? So you can think how human to learn. So suppose there is a new thing, right? You want to learn the new thing. In general, it is impossible to learn the concept precisely. During your learning process, you make mistakes, which is the error in the machine learning field. Even though you can learn using all the information that you have, still during the learning process, human makes mistakes. So that is why we call it a generalization error. So how can we define the error in the machine learning field? So let us take a look at the equation 2.4. So here C is the target you want to learn, and H is the knowledge returned by your machine learning algorithm, and X is the input that you feed into your algorithm. So if H is equal to C, that means you learn precisely. However, that is not the case, because we do not know C, we do not know the distribution, and we cannot use the entire population to train the model. Therefore, you always make mistakes. You always have error. So if this event, your result is different from the target, then you calculate the probability of this event. Sorry, that is your learning error. That is a generalization error. In other words, you can calculate the expectation, where here 1 is an indicator function, which means the event omega happens, then you take 1. Otherwise, it is 0. So suppose we only consider the here, for this introduction, we only consider the output space contains 2 different values, 0 and 1, which corresponds to the binary classification. For instance, if you want to decide whether the email that you received is the email that you want or it is a spam. So it is a binary classification problem. So right, so if the result that you learn is different from the target, then you have 1. Otherwise, you have 0. Then you collect you calculate the expectation of this function. That is your error. So that is how we calculate error in the for the machine learning field. However, as I just mentioned, you do not know C, you do not know the distribution C, and you can't use the entire population to train. Therefore, this generalization error is very difficult to calculate. However, we can use a different concept, which is called empirical error, based on the sample, the specific sample you choose, which just the average error over the sample. So that is called the empirical error. So it is so you can think when you take the expectation of the empirical error, you have the generalization error. So you can think the empirical error is just a instance or subset of the generalization error. So with these two different errors, how can we define the machine learning problem is learnable? Or how can we say that, okay, you have a result generated by your machine learning model, and can we trust that the age is the thing that you want to learn? One way is to calculate the differences between the two errors. So let's first define whether the problem is learnable. So you do not need to focus on the details. You just need to look at the equation 2.3. So H is the result returned by your machine learning algorithm. S here is the sample you use to train the machine learning. So given the S and H, you have a learning error. So obviously you want your learning error to be very small, which is epsilon. So this event having a very small training error, if this event has a large probability, then you can probably believe that the problem is learnable and the result generated by your machine learning model can be trusted. Right. So I think it is. So this is how we define learnable or not in mathematics. So this is the key point behind all the mysterious code or machine learning algorithms. So right now, so because as I just mentioned, you can't calculate this term, but this term is really matters in terms of you want to learn a concept precisely, because this is the generalization error using the entire population. However, you can't get it. But when you use a specific sample to get an empirical error, obviously you want this empirical error using this specific sample, which is a subset of your population, to be as close as possible to the generalization error. That's why we have the equation 2.5, the generalization error, generalization learning bound. With this bound, we can be sure that the results generated by your machine learning using a specific sample is probably correct. It's probably can be trusted. It's probably the concept you want to learn. So basically, this inequality tells you that you have a machine learning algorithm written in some kind of coding language, for instance, Python, and you can search a age. So the generalization error returned by the age using the sample you choose, the difference between this one, the empirical error, and the generalization error is greater than something. So it is. So that means this inequality means that you have a huge difference between the target error and the empirical error you have using the data set S. However, this event, large error difference, this event has a small probability. So that means these two, the difference between these two is very small, right? And you can see this term on the right-hand side, the bound of this probability can be calculated because here epsilon is just some number greater than zero, between 0 and 1, and m here is your sample size. Here, m here is your sample size. And h is the this term here is the cardinality of the hypothesis. So basically, it tells you that how many little h in this set. So as you can see, when you increase m, your sample size, this value decreases. That is why when you use large sample size, you would have smaller training error. So this equation basically is the foundation, the very foundation behind those machine learning algorithms. One problem is the calculating the cardinality of h, because sometimes this set is not finite. It might be an infinite set. Therefore, you can't really calculate log of this term. So we can try to change this term such that this boundary can be calculated when you actually implementing some machine learning approach, which is called the Hartmark complexity, which captures the richness of the family of functions by measuring the degree to which a hypothesis set can fit random noise. In other words, the Hartmark complexity can be used to derive data-dependent upper bound on the learnability of a function class. So intuitively, a function class with smaller Hartmark complexity is easier to learn. In order to calculate this Hartmark complexity, we need to introduce the loss function. So I believe you all know this one. So it is just the difference between the true value and the value you learn from the learning algorithm. So the empirical Hartmark complexity can be calculated precisely using this one. And here, sigma is just some random number you don't need to pay attention to. Then the expectation of the Hartmark complexity is the generalization Hartmark complexity. Then we can prove this inequality using the Hartmark complexity. So as you can see here, the second term comparing with the previous one I just introduced, the second term is replaced by the empirical Hartmark complexity, because at some cases I just mentioned, you can't really calculate this term. However, this one can be somehow calculated. Therefore, if you move this term to the left, you will have the learning bound here. This term, you will have this learning bound. Therefore, you can see for a machine learning model that you want to implement, you can calculate the learning bound precisely. And still here, right? When you increase the sample size, you get a smaller learning bound. Still, sometimes, for some cases, even the empirical Hartmark complexity is difficult to calculate. Therefore, we can further simplify this equation by introducing the growth function. Because we want to use this concept VC dimension to replace the second term. Because the VC dimension is nothing but combinatorial measure, which is much easier to calculate than this term, obviously, right? Because it's just a combination of your hypothesis set. The element inside, simply speaking, it is just the different combinations you could have given a hypothesis set. So you can see here that the growth function is just the maximum number of distinct ways in which m points can be classified using the hypothesis. Then by using the growth function, we can define the VC dimension, which is given by this equation. Then we can use the VC dimension to define the generalization bound, which is given by this equation. So as you can see, the second term is replaced by the VC dimension. So D here is a VC dimension because it is just a combination. So D can be calculated easily using the growth function. E here is just a mathematical constant. So as you can see, if you move this term to the left, the bound on the right can be precisely calculated because you know m, you know d, and you know e, and delta is just some small number. Right. So let's see an example. So suppose you are using linear regression, you can calculate these learning bounds. Because of these learning bounds can be calculated precisely or can be proven precisely. That is why when you use the linear regression, you do not need to worry about the results generated by the linear regression. You can simply trust that the h returned by your linear regression model is the concept, is the target concept you want to learn, and you can be sure that when you increase your sample size, you will have a better results, better h with a small error. And also using the same technique, for instance, you can also prove that in the reinforcement learning, which is very popular since the DeepSeek R1, you can always find a policy pi primes such that under this new policy, the value function of the reinforcement learning is better than the value function using the previous policy. And another example would be a special case of the reinforcement learning, which is the Q learning. So you can always prove that the Q eventually converges to the optimal value Q, which is the optimal solution using the reinforcement learning. Right. So these are the brief introduction about the mysterious mechanism behind machine learning. So I hope this could help you to understand a little bit about the fundamental things about machine learning and why, when you talk about machine learning, why it is different from statistics. Why in machine learning field, usually you do not use statistics to evaluate your machine learning model, because to my knowledge, using these learning boundaries, such as Hartmark complexity, VC dimension, it is very difficult to prove for the non-linear machine learning models, such as deep neural network. So to my knowledge, I think some scholars at Princeton University, they proved under a very simple structure of the feed-forward neural network with a very specific activation function. They proved the Hartmark complexity and the VC dimension. So now I want to move to the second part of the talk. So the machine learning in financial modeling. So model analysis of financial markets centers on the following definition of a price derived from the generic optimality condition of an investor. So the price is the expected value of the discounted future payoff of your asset, conditional on the information that you can have up to time t. Because the information set, for the information set, you can't have future information. Therefore, it is only up to time t. And for the payoff, it is the future payoff, not the payoff at today. So in other words, prices reflect investors' best guesses for the discounted future payoff shared by an asset. Therefore, prediction is a fundamental and important topic in financial modeling utilizing machine learning approaches. And we can easily see that for modern financial modeling, the information set could be huge. For instance, you can even use those Twitter information to train some machine learning, to train some trading strategy model using machine learning technique. Suppose asset price is the expectation of future outcome, then the mathematical tools to study price are forecasting models, because you want to forecast the price or forecast other variables in the financial modeling. Therefore, some functional form is needed, where xt here is the input or the features you can think, and theta is the parameter inside your functional form, and you need to somehow estimate this parameter. And for machine learning model, for financial modeling, the functional form could be very complicated. Therefore, roughly speaking, machine learning in finance includes a diverse collection of high-dimensional models for statistical prediction combined with a regularization method for model selection and mitigating of overfit, and efficient algorithms for searching among a vast number of potential model specifications. There are some challenges in financial modeling using machine learning. The first one is the size of data, of your training data. It is quite different from using, for instance, large language model, in which in general you have a huge data set. But in financial modeling, usually you face a very small data set. For instance, when you go to stock market, you want to buy a stock, but you can see some stocks are not very is not very liquidate, right? There isn't the trading activity for a certain stock is not very frequent. Therefore, even you want to buy or you want to sell, there isn't stocks you can buy or sell. So for those stocks, or for those kind of financial assets, you usually face a very small data set. The second one is the financial data is very noisy, which means when you collect a huge size of financial data to train your machine learning model, you have to do some data processing first to clean the data, because the data contains many noise, which is useless in general, and it will deviate your training from the true value that you want to seek. So the third one is investors learn and markets move, right? Because every day's market is different. This creates a moving target for machine learning prediction models. Previously reliable prediction patterns may be arbitraged away. So I think that is quite obvious. There are different tasks that we can use machine learning to predict in financial modeling. For instance, price prediction, financial asset pricing, constructing trading strategy, risk estimation, portfolio optimization, or financial detections for financial fraud. So here, this is an example using deep Q learning to trade VIX futures. As you can see, this plot basically tells you that given using the current market condition, what is the best trading strategy for the VIX futures. As you can see, the machine learning model can be used for constructing trading strategy. Another one is the annual percentage yield prediction. So we use different machine learning models to predict the annual percentage yield, which is, you can think it is a reward for the liquidity provider of the Uniswap liquidity pool, which is a liquidity pool for for cryptocurrency trading activity. So let me introduce some key variables you want to model in the machine learning technique. So you only need to remember that BT here is a standard Brownian motion, which is a stochastic process defined by these properties. So using the Brownian motion, standard Brownian motion, we can write the change of the stock price in this equation. So the change of the stock price can be decomposed into two parts. The first part, you can think it is the expectation or the average value of the change. And the second part is some randomness. So because you can't really predict what the price would be for tomorrow, right? Therefore, you need some randomness, so which comes from the second term. So by using Ito's lemma, you can solve this equation such that you can get a precise analytical expression for the stock price. So in a discrete time, we can rewrite this equation in this way. So you can see on the left, it is nothing but the return for the stock, right? Because you have today's price and you have a future price. So you calculate the differences between today's price and the future's price divided by today's price. That is your return. So this equation 3.4 tells you that the return can be divided into two parts. One is the expectation of your return. The other one is the randomness, which is called volatility in financial modeling. The sigma, I believe you heard this term. So sigma here is the volatility, and epsilon here is just as a standard Gaussian random variable, which is the randomness, the source of the randomness. So from this equation, you can see there are four important fundamental variables in financial modeling: price, return, the expectation of return, and risk volatility. So yeah, so here it is a plot for the price and the volatility. So it's ST and sigma. As you can see here, when you observe big jumps in the price, here, for instance, you would observe a huge volatility. If the price doesn't have huge jumps, then you can see the volatility is, in general, it is very low. Therefore, volatility could be used as a signal for trading. Right, okay, let me show some examples. Let me see, where is it? Yes, I think it's here. Right, okay. So there are two important Python libraries you could try. The other one is called TA lib. So it is basically a Python library for technical analysis. So it contains quite many different commonly used factors used by those technical traders. Another one is Yahoo Finance. You can download quite many different data. Even it has option data. So I wrote some functions to download the Yahoo Finance data, stock price, and use the TA library to calculate some factors I want to use to be the feature for the prediction later. So here you can see this is the plots that I generated. Okay, so let's see. The first one is I want to use the gradient boosting regression tree to predict volatility of stocks. So this is the oh, 1 second. So this is the daily price of Apple. So oh, 1 second. So Right. As you can see here, there are quite many different factors we can choose from the data frame. Here, yeah. So this is the return of the functions that I wrote before. So it returns price, different kind of a moving average, which is the mu term that you saw in the previous slides, and also other indicators used by the technical trading, and also daily volatility. So I'm going to pick some factors from this table to be the input space for predicting volatility. Right. So so these are the factors I picked. You can see the price, different moving average, and different indicators, and the daily volatility. So there are 14 different different columns. So the prediction is that you want to, for instance, you want to predict tomorrow's price using today's price. Therefore, the functional form would be the price is equal to some function of yesterday's price and other factors at t minus 1, right? So here, these are the factors I picked. Then, 1 second. We need to create the input space. So because you can see it is a very long time series, so I only pick part of it. I didn't use entire data because in general speaking, it is not always the case that you use entire data set is a good idea, because you can see from this plot here, it is a good example. You can see here, this is a huge jump on the price. That means if you estimate if you create a prediction model using to fit this time period, then the model you've trained using this data might not fit for this data point, because you can see here it is a huge jump. It is called regime changing. So in general speaking, when you see those regime changing events, you need to reevaluate or retrain your data, or re-estimate the parameters inside your model. Therefore, you have to pick. So so here I didn't use the entire time series. I only used a part of it. So you create the input space X using all of them from this data frame, and you pick the first column to be the output space, because this is the price you want to predict. You pick the very last one, which is the volatility you want to predict. Right, then we can write we can build our regression tree model. So the model is from the scikit-learn, by the way. So first you need to create a hyperparameter, which is the parameter of the machine learning model. It is not the model of the regression. So there are different hyperparameters. When you do the machine learning model, you need to create a grid search to search different value or different combination of your hyperparameter. As you can think, so for one combination of the parameter grid, you can think it represents one little h in the previous slides. So it is one element from your hypothesis set. So then we need to define the regression model. So these are some parameters to store the optimal value of the regression tree. So this is the function that we need to use from the scikit-learn, and we are going to use the Huber loss function, not the absolute loss or the mean squared loss, because the Huber loss could avoid how should I put it? So it could avoid the things that you do not want brought by the outlier of your data. Then another important thing is you need to use parallel computing to do the search, because searching among different combinations of the parameter is very time consuming. Therefore, you have to use the parallel computing, and if you can even write code using CUDA to use the GPU to increase the searching speed. But here I'm simply using the parallel computing, and also you need to do the cross-validation, which means you divide your data into different subsets. For instance, you divide the entire data into 10 different subsets, and each time you only use 9 of the 9 subsets to train, and use 1 to validate your model. Then we need to compile the model. So here is the grid search and train, right? So after this one, you pick the best hyperparameter combination, and you use that one to train the model. Okay, let's run it. So let's wait a little bit, and after running, so it is running. We can keep going. So after running, you want to test. So you get the test data from the data frame, and then you use the trained regression tree to test on the testing sample. Then you plot and see the results. These hyperparameters, some hyperparameters are just the other parameters for the regression tree, for the tree model, and some hyperparameters are for the regression inside the tree. So for instance, how deep you want to pick for the tree. Right, okay, let's see the results. So the blue line is the training data, and the orange line is the predicted training data. So basically, this plot tells you that it is a in-sample test. So it should be good, because the training data and the testing data are the same. Then this is the out of sample test, right? So this is using the trained model applied on the data set that is not used for training. So you can see the blue line is the target, the orange line is the result generated by the machine learning model, the regression tree. So you can see in general, it is not bad. And this is the entire time series. Right. So this is one example because volatility is really one of the most important variable in in financial modeling, for instance, especially for option trading, because when you price option, you need to create the entire volatility surface, such that you can use those volatility surface to calculate. Right. Okay. Let's see another one using the LSTM to predict the stock price. We still use the same data set, but this time I'm going to use a different. We pick different input space or different features. So this is the put. This is the price, and these are different moving averages with respect to the price. We can then we need to construct our input space. One thing for the LSTM is that because the LSTM is good at dealing with time series, because usually time series model requires some past information, because it is how should I say, it is past dependent in general, because in the historical information could contribute for your price prediction at time t. Therefore, you want to include past information, not only yesterday, but maybe the day before yesterday, or maybe 10 days before. Therefore, we need to first create a input space. So the input space would be this one. Right. So for instance, suppose you have two different features. You want to use the features at T1, T2, and to predict T3, right? You can see here it is not only T1, but T1 and T2. Then you want to T1, T2, T1 and T2 to predict T3. And then you want to T2, T3 to predict T4. So we need to create this input matrix first. So creating this input space is not a hard thing to do. You just need to write a for loop to form this special input shape for the LSTM. By the way, I'm using TensorFlow, so I'm not quite sure the shape of the input for LSTM using other neural network model, for instance, PyTorch. So this is the structure for the TensorFlow. Then we can set the input space. Then we build the neural network. So we first, it is a sequential model, right? And so the first thing is the input layer. The input layer, the shape of the input layer has to be the same with your feature space. Therefore, you create the input layer. Then the second one is the most important one, which is the LSTM layer. So you simply use the LSTM given by the TensorFlow, and you can choose what kind of activation function would be, and how many units. Then after the LSTM layer is just the dense layer with a ReLU activation function. Then the last one is the output layer, because here we are going to predict the price. Therefore, the activation function of the output layer should be linear. Then we can set early stopping, and we can save the best model during the training or during the validation. Then we compile and we run. the TensorFlow, the neural network. So here I split the training data into two parts. So 90% of the data are used for training, 10% are used for validating. And the batch size, the epochs are 133. So let's run this model. Then after running the model, still we need to test. So this is the lines for testing, and also eventually we want to see the results by plotting. Right, as you can see here, right, the initial mean absolute error is 67, and using the current structure of the LSTM that we just created, you can see during the training the error is decreasing, which means this might be a good structure for the LSTM, and also splitting the data into two parts in this way would be good. Right. Okay. So it is still running. We can wait for the results. While if you have questions, I'm happy to answer.